All right, Chem 11, our next topic, decomposition reactions and determining chemical formulas from them. Basically, we'll be making sense of the leftovers today. To do this lesson properly, what will we need? Well, half of it is theory, so you're going to need your brain. The other half is going to be practical. We're actually doing some of the calculations. I'm going to lead you through them. It would still be helpful for you to have your periodic table 3000 Mendeleev edition and the Calculator-Matic 3000. Notice it's saying hello to me. How smart is that machine? And it's, of course, the solar-powered edition. So when the solar flares hit the Earth and knock out all the power, you can still do your chemistry. All right. So let's go through, start talking about some of this stuff, and see what makes sense. I'm going to grab a chair. All right. So, decomposition reactions. Basically what we're going to be doing here, there are methods of determining chemical formulas of an unknown compound by using decomposition reactions. Right? So basically what we'll be doing is, right, we'll be looking at the substances that are left behind from an unknown compound when it decomposes. Sometimes these substances that are left behind, right, the products, the leftovers after everything's been broken down, they're trademark compounds, right? And what this means is that we can use them to determine what the original substance was. It's like a fingerprint. The breakdown of this would only leave that amount of this and this. The breakdown of this molecule would only leave that amount of this and this. So for example, a decomposition is AB breaking down into A and B. We might not know what the exact formula of AB is, but if I know the amount of A and the amount of B that were formed by the breakdown, I can go backwards and figure out the formula of compound AB. Is it AB? Is it A2B? Is it A2B3? Is it A4B3? Who knows? The amounts of these products that are formed in the decomposition reaction will tell us what the original formula is here. So we'll be using the amounts of A and B that are left over from the reaction once it's all being decomposed to figure out the correct formula for the initial reactant, AB. Excuse me. So we're going to be looking at three types of decomposition reactions, all right? And again, the products are going to help us determine what the original reactant was, the original formula. So we're going to look at the analysis of oxides. If you remember, an oxide is anything that has an element and oxygen, right? Any element plus oxygen together in a compound, that's an oxide. So we can identify oxides when they decompose to form, obviously, oxygen and that other element, whatever it happens to be. We're also going to look at today the analysis of hydrated salts. Right? A hydrated salt, if you remember when we were doing our names and formulas, is just an ionic compound like calcium chloride or copper 2 sulfate, just an ionic compound, but in crystal form, it has water molecules locked in with it. And what we can do is we can figure out the ratio between how many water molecules every salt molecule is carrying with it. So is every salt molecule carrying 5 waters with it? Is every salt molecule carrying 6, 7, 2? How many waters are locked in with every salt molecule? And of course, we won't cover it today, but we will in another lecture. Carbon-hydrogen analysis. This is where we take a hydrocarbon fuel with the formula CH something, right? And I put X and Y in here to represent numbers. So it could be C2H3, whatever it happens to be. And we look at the amount of, well, if you think about a combustion reaction and burning a hydrocarbon, we're bound to get carbon dioxide and water from that. So we'll be using the water and the carbon dioxide produced when we combust these hydrocarbon fuels to go back and tell us what the exact formula of the hydrocarbon fuel was. All right? Today, we are going to go over these first two, analysis of oxides and analysis of hydrated salts. This one we'll do in the next lecture. All right? So, analysis of oxides. Now, if you remember, I'm just going to quickly erase our board here. An oxide is simply any element with oxygen in a compound. Now the ones that we're going to be using today, when we look at oxides, it's going to be a metal and oxygen together in a compound. All right, so when that breaks down, we'll have our metal oxide. And it's going to break down, and we're going to get solid metal and oxygen released. And the oxygen will be a gas. All right, the oxygens will start to pair up and form O2. So that's what that looks like. Now, when we break these metal oxides down, we often employ heat. So we heat things up, and that helps the two separate into the solid metal and the oxygen gas. All right, so it looks kind of like that. Some real life examples: silver oxides can break down, add a little bit of heat into silver and oxygen gas. And zinc oxide, if we add some heat there, we'll get zinc and oxygen gas. Because we're adding heat, they're called thermal decompositions, right? So whenever we see that little triangle, we know, remember from earlier lectures, that means heat is added. So this is a thermal decomposition. In fact, all of these today and tomorrow are thermal decompositions. We're going to be using some heat to separate the two components. So then what we do is we use the amount of this. Now, we can get the mass of that and the mass of this produced, and we'll use these masses to figure out the formula of this. So again, the products will work backwards with these two things to get the formula of that. All right? So here's example number 1. I'm going to leave it up in the corner here. Now this is on the PowerPoint on your D2L page. I just added this today. So there's our first example. I'm going to set that up. So it says that we have a silver oxide. So silver oxide means it's like this. There's silver and there's oxygen. We're going to heat it up, break it down via thermal decomposition, and we're going to get silver and oxygen out of this. All right? Now the values that are given in this question, I'll put in black here. It says we have 4.626 grams of this. We heat it up. Now the oxygen would go up into the air, but this would be a solid. Silver is a solid metal. So they weighed this, and they got 4.306 grams, and this stuff went up into the air. It wasn't given in the question. It's hard to weigh that when it escapes into the atmosphere. But you're probably already thinking it's pretty easy to find the mass of this, sir. You just take the two of them together. The Ag and the O together were this. The silver represents that part of it. So if I take this number and subtract this number, I'll get this number, right? So we'll do that very quickly. This minus this, if I put that into the calculator, that subtract that, I end up with 0.320 grams of the oxygen. All right? So now we've got everything we need. And our steps are just like they were before. If you remember when we were determining formulas before, right? Our steps were this. The first step, I had to get the mass. Well, I've got the masses. I've got grams here, and we just figured out grams there. The second step is grams being converted into moles. Well, I'll use my periodic table 3000 to turn this into moles and this into moles by using those molar masses, which are the same as the atomic masses on the periodic table. And then I'm going to divide by the lowest mole number again. All right, so I'll leave those there. Hopefully I've got enough space here where I can do it in the bottom area here, and I think I do. Right? If we were in class and I had this on the board, I'd use this space here. So let's go ahead and put our two elements in, Ag and O. All right. Ag is 4.306 grams. That was given in the question. The oxygen we figured out was this. All right. So we've got step one done. We've got the grams of both of the products here, both of the elements. Now we're going to convert them into moles by dividing by the molar mass, which is on the periodic table. So if I look very quickly, silver is 107.87. And oxygen, of course, is 16. We've been using oxygen a lot. I remember that now. And this is grams per mole, grams per mole. All right? And then I'll divide that out. I'll use a calculator, Matic 3000. This ends up being 0.040 moles. This one ends up being 0.02 moles. So I've converted them both into moles, and now I have to divide by the lowest mole number. 0.02 is lower than 0.04, so I'm dividing them both out by that. Moles divided by moles will cancel out. I'll have no moles. This will be 1, and this one obviously will be 2. Therefore, my empirical formula is Ag2O, and I don't have to show the 1. So again, if I go up here, this would have been a 2, that would have been a 1. We don't show the 1, so there's our final answer. All right? Easy enough? That's all it's to it. So a lot of this stuff relates back to earlier learning. When we first started doing formula determination, the steps are still the same. It's just how we get the numbers. It's through a decomposition reaction. All right? So pause the video now. You can get this into your notes in here. It goes along with example 1. That's what this is. So get this down, pause the video, and I'll set up our next question. And I will try to leave this in place for us. All right. Example 2 in our oxides. So we're still doing oxides, analysis of oxides. And this one says I've got a 7.59 gram sample of an oxide of manganese. Manganese on the periodic table is right here. It's Mn. All right? Be careful, common mistake. People see manganese and they think magnesium. All right, and that's going to alter your molar masses. So it's Mn, we don't know that number, and O, we don't know the subscripts in the formula. So these things right here, we don't know those yet. All right. So it says a 7.59 gram sample of that. We heat it up. So it's a thermal decomposition. Put my little triangle in there for accuracy. And it says we get, obviously, manganese metal and oxygen. And the manganese is 3.76 grams. That would be a solid, easy to weigh. The grams of this we don't know because it goes in the atmosphere. It wasn't given in the question. But again, it's very easy to figure that out, right? All we have to do simply is take the two of them together. So when Mn and O, manganese and oxygen, were together, it weighed this. You take away the manganese and you'll get the oxygen. And when we subtract those, it ends up being 3.83 grams of oxygen. All right? So this was the two of them together, and there they are separately. So, again, let's follow our steps. I'm looking for manganese and oxygen. The two elements in the formula. Masses, do I have their grams? Yes, I do. I have it right here and right here. So I'll transfer that over. 3.76 grams, 3.83 grams. Then I'm going to convert them into moles by dividing by the molar masses, the same as the atomic masses on the periodic table. So I divide by their molar mass. Manganese is 5494 grams per mole, and oxygen is 16 grams per mole. All right. Now I know this will form, technically it forms oxygen gas, which would be 32. But again, this is for all of, think of this mass as the oxygen atoms, all the oxygen atoms that are produced. All right, so don't use 32 here. Use 16. Use what the element is, 16. All right? So don't think of it as O2. That's why I purposely didn't write it in there. So grams divided by grams will be no grams, and I'll be left with moles. And this one is going to be, the manganese is 0.068 moles. And the oxygen is 0.239 moles. Common mistake. People forget this 0 and I see them dividing by the 0.239. Remember that 0 there makes the 6 smaller than the 2. All right, so this is actually our smaller one here. It's one of those mistakes where people slap their head and they go, oh my God, they do a face palm, right? Can't believe I made such a stupid mistake. It happens. Best to make them now and be aware of them now than to make them on a quiz or a test, right? So that one I know is going to be 1. Moles divided by moles will be no more moles. And this one ends up being 3.5. This is a problem we've seen before. When it ends in 0.5, what do? We obviously can't have 3.5 oxygens. So we have to do that extra step. All right, so I'll do it down here. Mn was 1. It behaved. Oxygen, not so much. When it ends in 0.5, what do? We multiply by 2. But we have to do both of them. So the 0.5 we'll get rid of by multiplying by 2. So it's an extra little step. It's not listed here, but we've come across it before. And that will make the manganese 2 and the oxygen 7. Whenever we get one of these decimals in here, it means there's no 1s in the empirical formula. So therefore, my empirical formula in this case is Mn2O7. Easy enough? All right, so that's example 2 done. Again, you can see we're not reinventing the wheel here. It's pretty simple stuff once you kind of walk yourself through it. We've done this sort of stuff before. We've done all these calculations. We've done these steps. So let's move on to the next question, or the next group, which is the hydrated salts. Excuse me. If you need to, pause the video right now, get this down, pause the video, and I'll set up for the next section. So the analysis of hydrated salts. Now you remember hydrated salts, those were simply an ionic compound, right? Salts are ionic compounds that have water molecules locked within their crystal structure. And you can have various amounts of water. Not every hydrated salt has the same amount of water. In fact, some of the same hydrated salts, like calcium chloride, some can have 1 water with every calcium chloride molecule. Another form can have 2, another form 4, another form has 6. So each one has its own unique number with it. And even some of the ones, like I just said, calcium chloride can have several variations. But they're all the same in that they have, right? A hydrated salt is simply an ionic compound with a certain number of waters. This ionic compound is the salt, and this is the hydrated part, right? And we name them. If you remember, we did these names and formulas. The number that goes here, we use those same prefixes that we do with covalent compounds, like mono, di, tri, tetra, penta, hexa, hepta, that stuff, right? So what we do here is the same sort of thing. So here's another example of this reaction. So we have calcium chloride hexahydrate We add some heat. I didn't put the little delta triangle there, but it's a thermal decomposition. We added heat. We get calcium chloride and water from it. So the salt and the water, they split apart. The water will evaporate into the air because we're using a significant amount of heat. So it's water vapor, not water liquid. The salt, once all the water is gone, is just a dry form of the salt. It's not hydrated anymore, and we call it anhydrous, right? The AN in front of it means that it's not hydrous. It's not hydrated, so the water has been removed. So we look here, what we're looking for in this type of a question or reaction is the number that goes right here. We're trying to find out how many waters go with each of the salt molecules. The salt is always going to be a 1. We'll have 1 molecule of salt. We're always looking for how many waters are locked in that crystal structure. So we're always trying to find the X here in this type of a problem. All right? So in this, right, in this example up here, calcium chloride hexahydrate, this is my hydrated salt right here. Calcium chloride would be my anhydrous salt because the water has left it, it's gone. And this is my water which would evaporate into the air. So hydrated salt, anhydrous salt. All right, without the water, it's separated, 2 different things. All right, so let's do some problems here. Oh, sorry, I forgot I had this in here. So here's an example. This is a form of copper sulfate. So the hydrated salt, a lot of them have their crystals and they have brilliant colors. Like, look at how nice that blue is, right? You put this thing under a bit of heat. Over a Bunsen burner would be enough heat. Doesn't have to go like into a blast furnace. A Bunsen burner would provide plenty of heat. And this is the anhydrous or dry form of the salt. All the water has been removed. So you can see it just kind of looks like, well, it looks like regular table salt in a way. It's not as nice as that, you know, at all. And a lot of the hydrated salts kind of follow this pattern. They've got this great coloration, and then when you take the water away and get the anhydrous form, it's much more duller, or a whitish color, pale gray even, right? Now, if I add water back to this, so if I could take a glass of water and pour it back on here, what happens is it will start to hydrate again. Or if I leave it out in humid air, it will actually absorb moisture out of the atmosphere, right? So you can see here, there's my hydrated salt. If I start to take water and add it, I'll get my hydrated salt back. The crystals reabsorb the water, all right? So let's take a look at our first one here. Excuse me. I think I'm going to move these steps very, very quickly up to the top corner here. So steps 1, we need the mass. 2, the mass has to become moles. 3, divide by lowest moles. All right. So this are steps for formula determination. I just moved them really, really quick. And it says here, when 5.742 grams of hydrated magnesium sulfate is heated until all of the water has been released into the atmosphere, 2.801 grams of anhydrous magnesium sulfate remains. Determine the formula of the hydrated magnesium sulfate. So what I have is magnesium sulfate, which is MgSO4 dot, and I've got H2O. So I've got a hydrated salt, right? This number in here, we don't know. I don't know what that is. It could be dihydrate, heptahydrate, pentahydrate, I don't know. We heat it up, so a little thermal decomposition, and I get 2 things. I get MgSO4 and I get water. So I separate this from that. And it says in the question, I'll put it in a different color so it stands out. It says we had 5.742 grams of this. We heated it all up. We ended up with 2.801 grams of that. We don't know the grams of the water yet. But again, we kind of do, right? You guys are you've caught on to this by now. This is the mass of both of these things together. If I take this out of it, I'll be left with the mass of that. So this, subtract that, will give me this. And when I do that, I end up with 2.941 grams. That grams looks like a 9. I wrote a little high. So again, I took both of them together, this number right here. I subtract this from it, and I'll be left with my water. That's what I'm going to bring over here. So my answer we'll do in blue, MgSO4. It's a terrible looking G, but we'll live. And I'll put down my masses. Step 1, get the masses. I got the mass of both products here. So 2.801 grams and 2.941 grams. The next step is divide by the molar mass and turn my masses into moles. Now, the molar mass for these I'm going to get by adding the components. So I'll go to the periodic table, find the mass of magnesium, a sulfur, and 4 oxygens. When I do that, and I add them all together, it equals 120.38 grams per mole. So this number is the molar mass of this formula. 1 mg, 1 s, 4 o's, using the periodic table values. H2O I get by adding 2 hydrogens and an oxygen, and that one's 18.02 grams per mole. I divide those using the Calculator-O-Matic 3000, and I end up with 0.023 moles of that and 0.163 moles of that. Don't forget your units. Don't want to throw away marks. Grams divided by grams is no grams. I'll be left with moles. All right, so I've got my moles. Now I divide by the lowest mole number. That's this one, right? This is 0.1. This is 0.02. So this is my lowest one, this top one here. That one will equal 1. That's the easy one. And this one, when I divide it out, take this and divide it by that, I get 7. Nice and even. Again, if it's 7.02 or 6.99 because of rounding, it's 7. 7.33 or 7.5 I can't ignore, but 7.01, 7.02 I can, that's 7. All right, so therefore, the formula for the hydrated salt is MgSO4. We always said we'd get a 1 for the salt. This is my salt. We got a 1. And it's going to be the 7 we just figured out here. So it's magnesium sulfate heptahydrate. Magnesium sulfate heptahydrate, MgSO4, 7H2O. All right, so that's example number 1 done to the hydrated salts. Pause the video right now. Get this stuff down into your notes if you need to. And I'll get on with our next question. Number 2. This whiteboard has been invaluable to me, I'll tell you. One of the best buys. So, number 2. It says when 3.62 grams of anhydrous calcium chloride, so it has calcium chloride, and there's 3.62 grams. And it said anhydrous, which means the water's not with it. So it's just the calcium chloride. When it's left in the open air, it absorbs 1.17 grams of the water. Right? We said if the air is humid enough, the salt will draw in some of that humidity, some of that water from the air, and form the hydrated version of the salt again. So, determine the formula of the hydrated salt. So what we're looking for again is CaCl2 dot H2O, and we're looking for whatever that number is. Now in the last question, they gave me the mass of this, but I have the 2 things I need already. My salt is 3.62 grams. My water that was absorbed is 1.17 grams. So we didn't have to do that little first calculation to find something. They gave me the anhydrous form of the salt, which is this. They gave me the water, which is that, and we're good to go. We got the grams already. Now we've got to turn the grams into mole by dividing by the molar mass. Water, I just remember, was 18.02 grams per mole from the last question. So that one I kind of remembered. I got to calculate this one. So 2 chlorines, 35.45, plus another 35.45 is 7090, plus 40.08 from the calcium is 110.98. So that's the molar mass. Again, I just 2 chlorines, 1 calcium, add up their masses on the table, periodic table. Finish on my calculation. This is 0.032 moles. This is 0.065 moles. So I've done this. I've turned them both into moles. Next, divide by the lowest mole number. That's this top one, 0.032 moles. And I divide them both by that. Moles divided by moles will be no more moles. And this is a 1. That's a 2. So therefore, the formula of the hydrated salt is CaCl2. We always said the salt would be a 1. And we have 2H2O. So this is calcium chloride dihydrate. CaCl2, 2H2O. Calcium chloride dihydrate. All right. Now, carbon hydrogen analysis, that will be in our next lecture, which I'm sure you can't wait for. But for now, I hope this made sense. Pause the video or get this into your notes. I hope it all made sense. If it doesn't, if you have any questions, comments, or concerns, or something didn't make sense, let me know through the comments section of this video on YouTube, or if you're one of my students, reach out to me through Edsby, and we'll get to the bottom of it. Anyway, I hope it was crystal clear. I'll talk to you soon. Bye-bye.